Today we're going to take a look at ray diagrams for thin lenses. There are two basic types of thin lenses. One kind of bulges outwards and it's called a convex lens, and one comes inwards like a cave, so it's called a concave lens. So let's use our ideas of refraction to determine how a ray is going to bend as it enters a convex or concave lens. So let's say we've got a ray coming in like so. It's going to hit that surface. Let's now draw the normal at that surface. So the normal would be approximately like so. I'm trying to draw that so that normal line is perpendicular to the surface right here. The ray is now entering a slower material. Glass is slower than the air out here, so it's supposed to bend towards the normal. So it would have gone straight. It's going to get closer to this normal line. So there would be right on top of the normal line. It's just going to get closer to it, something like that. And then it's going to meet this surface here. So we need to draw another normal line, and it would be about like that. Once again, I'm trying to make that line normal or perpendicular to the surface here. The outcoming line, it won't go straight. It's going to bend. Now it's going into a faster medium, so it's going to bend away from the normal. It's going to get, instead of here, it's going to get farther away from the normal. So it's going to go roughly in that direction. So if it comes in parallel, it's going to bend towards the principal axis. And we could do another ray down here. It would come in and bend in a similar manner. So we call a convex lens. We also call it a converging lens because you can see that these two rays coming out of the lens are getting closer together. They're converging. So let's do the same sort of reasoning with the concave lens. There's the ray coming in. Normal would be roughly like that. We're supposed to bend towards the normal, so we're supposed to get closer to that red line on this side. So do something like that. I'll draw another normal line here, and this time it's supposed to bend away from the normal because it's going into a faster medium. So we want to get, instead of going straight, we want to get farther away from the normal. And we could do the same thing with another ray down here. It would come in like that, and it would bend and head outwards. So now you can see that these two rays are diverging from each other. They're getting farther apart. So this is called a diverging lens. So let's try to do a ray diagram for a convex lens. Once again, we're going to have three simple ray rules that we're going to use to do these ray diagrams. It's exactly going to parallel what we did for the mirrors. The big difference between mirrors and lenses, light bounces off mirrors, whereas light passes through lenses. So one of our rules before was to do with a ray that went parallel to the principal axis. Now in this case, this here is a converging lens, so we know that this ray should converge. It should come towards the principal axis here. And I'm going to put a little point right where the ray intersects the principal axis, and that's going to be called the focal point again. And any ray coming in parallel to the principal axis will go through that focal point, and that's our first rule. A ray parallel to the principal axis will pass through the focal point. Note that there will be a focal point on both sides of the lenses because both sides of the lenses are curved. So we might put one over here as well, and I want to make that at an equal distance as the other one. If this had been a diverging lens, we would have wanted it to diverge away from the focal point on this side. So to make your choice as to which focal point to choose, you really have to look at whether or not you want the ray to diverge or converge. Our second rule is our simplest rule. It says that if we take a ray and it passes through this center point on the lens, it's called the optical center. If it passes through the optical center, it'll just go in a straight line. No refraction at all. And we could do our little refraction diagram here. We'd get a little dog leg, but it would carry along in a straight path. So as long as our lens is quite thin, this rule works beautifully. So let's write down that rule. A ray through the optical center will pass straight. And then our third rule, this time we want a ray that goes through the focal point, and it'll be the focal point on this side. And you'll notice that if I pass through the focal point on this side, it will go parallel, and we should get a common intersection point if I've been careful. So we do get a common intersection point there. And once again, just like for mirrors, tip of the arrow goes at the intersection point and runs back to the principal axis. And then we always characterize the image using SALT. So its size in this case, well, it seems to be approximately the same size. But of course, if I brought this back here, this would become smaller. And if I brought this forward more, this would become larger. The attitude, well, this one's inverted. The location, opposite side as object and beyond the focal point. And the type, these are real rays of light intersecting at that point. So this is a real image. Okay, let's try to do a ray diagram for a magnifying glass. And of course, when you use a magnifying glass, your eye would be on one side and the object's on the other side, and the object's got to be close to the magnifying glass. Otherwise you don't get that magnified image. In fact, it's got to be in front of the focal point. So let's use our rules and see if we can work out what the image is going to be. So if a ray comes parallel to the principal axis, it's supposed to go through the focal point. And remember, there's a focal point on each side of the lens. Notice that this ray is coming towards the principal axis. So this is a converging lens. It causes that ray to converge towards the principal axis. Another ray that we could do is the easiest one, the one right through the optical center here. That one just goes in a straight line. So now you can see that we've got diverging rays over here. They would enter the eyeball, and the brain would interpret that those rays came in a straight line and would see the tip of the arrow somewhere back here where those two lines would extrapolate to. Now, we only need two rays to draw our image. If we want to do the third ray, it's a little bit tricky. You might think that if something went towards this focal point, then it would travel along the parallel axis. And you can see that this ray here, it's not like the other two, right? It's not extrapolating back to a point back here. It's crossing at that point. So in a sense, it's not like the others. The other thing is it's not bending towards the principal axis. It's not converging. It was heading towards the principal axis, and now it's going straight along the principal axis. So that's not correct. Our other option is to have a ray come from the focal point on this side, go through the tip of the arrow, and meet the lens, and then it goes parallel to the principal axis. So now you can see you've got these three rays, and if we extrapolate them all backwards, they're going to intersect at a point. So let's do that. There's one, there's two, and there's three. And I'm a little bit off. So this point on the arrow would show up as this point, this intersection point on the image, and our image would be like so. And then we'd characterize it, of course, With a magnifying glass, we're expecting a larger image than object. We see things upright in a magnifying glass. The image is on the same side as the object, but behind. So even though it looks bigger, the image looks farther away than the actual object. And then the type, of course, we're extrapolating rays back, so this is a virtual image. There are no real rays intersecting back here. Let's try a ray diagram for a diverging lens. So if we put a ray parallel to the principal axis, this is a diverging lens, so it's supposed to diverge from the principal axis. It's supposed to go in about this direction. So it's this focal point that we want to use. We've got a focal point on each side of the lens, so we always have to choose which one to use. This is a diverging lens, so it's got to be this one. So I'm just going to approximate here. It looks like it would go in about that direction there. So this should line back up with that focal point. Of course, your easiest ray is always the one through the optical center. And you've already got enough information to complete your ray diagram now, because you've got two diverging rays on this side. So if your eyeball were over here, it would receive diverging rays. It would assume they came from in a straight line, and you'd get your image right about here where this ray and this ray intersect. But let's try to do that third ray just for completion. So if we use this focal point, it came in like that, then we would go parallel to the principal axis, and you notice you're getting intersecting here. These two rays are actually converging on each other, whereas these two are diverging. So this one is not like the others. This one's not correct. Also note that this ray came in, it was heading away from the principal axis, and then suddenly it's running along the principal axis. So it's not diverging from the principal axis, it's really converging. So that's not correct. We've got to use the other side. So if we head towards this one, we would meet the lens right here, and that should go parallel to the principal axis. So now you can see you've got these three rays that are diverging in a consistent manner. So let's work back. One ray, the eye would interpret this ray as coming in a straight line, so it would come in that direction. This one would come in a straight line, and this one also in a straight line. So they're all converging right at that point. So the image would be right here, and we can characterize that again. The size would be smaller, the attitude would be upright, the location same side as object, and in this case it's in front of the focal point, meaning it's closer to the lens than the focal point is. And the type would be virtual. The brain was reconstructing there. These are dotted lines. There's no real light at that point. It's a virtual image. So let's take a look at how we could use a lens to correct for a vision problem such as nearsightedness. Here's how the eyeball basically works. If we've got an object that's far away, then we use the muscles in the eye to narrow the eyeball lens here. And what that does is, as the lens gets narrower, these rays don't converge as much. And what we want for a focused image is we want that point. We want the image point to exactly meet at the retina so that the object becomes focused on the retina. The retina is kind of like a screen at the back of the eye, and there's cells there. And these cells fire when they're hit by photons of light, and your brain is somehow able to interpret that and make an image. But it can only make a focused image if the rays are focusing right at the retina. So if you've got a close object, a near object, say up here, then you've got to use your eye muscles here to focus it at the retina again. Now, if somebody's nearsighted, that means they're able to see things that are near well, but they can't see things that are far away. So nearsightedness means good at seeing near. So right now we've got a near object. If the person tries to focus, they make their lens wider and wider, and they eventually bring it in focus. So everything's good. But if they have a far object, you can see that no matter how much they strain their eyes, how much they try to focus, they can't get that point on the retina. So to correct for nearsightedness, you'd like to bring these rays out a little farther so that they can focus back here on the retina. And you do that with a diverging lens. So now the rays diverge from the principal axis at that diverging lens, go through the eye lens, and now are able to meet at the back of the retina. So we can correct for nearsightedness. Somebody who's farsighted is able to see far objects well, but not able to see near objects well. Let's summarize the big ideas from the video. We started out by introducing these thin lenses, and there were two types. One that kind of bulged outwards, and the other was kind of a cave on each side. So these would be convex. They bulge outwards. These are concave. And what happens with a convex lens is that the rays will bend towards the principal axis. So they are going to come in and they're going to converge. So this is also called a converging lens. Whereas for the concave lens, the rays come in and then they move away from the principal axis, so that's called a diverging lens. Secondly, so we had these three rules. Once again, they were very similar to the ones we had for mirrors. Our first rule was that if the ray was parallel to the principal axis, it would go through F. And you want to choose the right F such that it's going to converge or diverge appropriately. So if we want these rays to diverge, we'd want to use this F. If we want these two rays to converge, we'd want to use this F. So choose F to converge or diverge appropriately. Second rule, very easy rule. If it goes through the optical center, it goes straight. No bending. And thirdly, if it goes through F, then it will run after the lens parallel to the principal axis. And once again, you have to choose the right F so that it's converging or diverging appropriately. So choose appropriate F. There's always two of them. And thirdly, we had two applications that we looked at. One was for a magnifying glass. And keep in mind for the magnifying glass, it's a convex lens and you've got the object in front of the focal point there. And your eyeball would be over here. And the second application that we looked at was nearsightedness. And in that case, we used a diverging lens in front of the eyeball that would bring the rays out a little bit so that they could be focused by the lens in the eyeball, and we get an image point right on the retina.
And that's all for today, folks. Thank you very much.